Well, it looks as though I lied. There is one additional section beyond the last section that we just went over. To me, this is one of the more interesting sections in the course. Something that I tell my students in the on-ground class a lot of times is that a lot of the material that we cover in this course, not surprisingly, you probably will not use in real life as a nurse or other type of healthcare practitioner. You probably will never be asked to balance an equation or to use the logarithm button on your calculator or to find the number of moles of medicine that you're giving to a patient. However, as you probably have seen, some of the stuff that we covered in this chapter actually shows up in medicine a fair amount. Positron emission scans and radioactive medicines. It turns out that half-life, so this concept that that radioactive isotopes will decay, and the amount of time that it takes for half of a radioactive isotope to decay is called half-life. The concept of half-life actually shows up in a lot of different medicines that are not radioactive at all. So just as a little bit of background, half-life shows up in medicine an awful lot, and this you probably will use in real life. As a bit of background, the abbreviation for half-life is the lowercase letter t and then a subscript with the fraction 1/2, and this just means this is chemistry and biology and medicine shorthand for half-life. And as I mentioned, it shows up in medicines a lot. It turns out that pretty much every medicine that is manufactured today is measured for how long it takes after you ingest it or after it's given to you, how long it takes to be eliminated from the body, how long it takes for you to pee it out or poop it out or have it be converted into something that is no longer the medicine. And usually the amount of time that it takes is measured in half-life. So usually when people have a medicine, they measure the amount of time that it takes for half of the medicine to be eliminated from your body. And pretty much every modern drug is measured in this way. And the reason that this information needs to be gathered is because when someone is giving you a medication, they want to give you enough of the medication so that it will do whatever it's supposed to do in your body. But if it's eliminated very fast, if it has a very short half-life, then they need to give you the medicine more frequently. And if the medicine has a very long half-life, if it doesn't leave your body for a very long time, then you should not give the patient frequent doses of that particular medicine, or else they might have an overdose. So half-life actually shows up a fair amount, almost in all medicines that I can think of, at least in all prescribed medicines that I can think of. And the idea is that different drugs, so different medicines, have different half-lives. And I will just show you a couple of examples. This paragraph here, you don't need to read the entire paragraph. However, this paragraph comes from the package insert or the prescribing information for a drug called atorvastatin. If you don't know what a package insert is or prescribing information, if you've ever gone to the pharmacy and picked up a prescription medication, they will usually hand you a box or a bottle full of pills, and there will come along with that a large sheet of paper with very, very tiny print, and it will list pretty much everything that's known about that drug. And almost always in the prescribing information, in that sheet of paper, they will list the half-life of the drug. Now, atorvastatin, many of you may know, its commercial name is Lipitor. Some of you may know that name. And Lipitor is used to treat high cholesterol. So it's used to reduce cholesterol levels in the blood. And if you read the prescribing information for atorvastatin, there is a sentence here that I've highlighted in blue that says mean plasma elimination half-life, so there's half-life, of Lipitor in humans is approximately 14 hours. So what that basically means is that if you ingest a pill of Lipitor, after about 14 hours, half of it is gone. Half of it has been eliminated from your body. It's either been broken down by your body or you've excreted it in some way. And so basically, by knowing the half-life, knowing that the half-life is somewhere around a day, you can make a reasonably good guess that Lipitor is probably taken either once or twice a day. And I believe most people probably take it once a day, because after slightly more than half a day, half of whatever atorvastatin you've ingested is gone. And so that's an example of Lipitor being measured, a very heavily prescribed drug, being measured as to how long it takes to leave your body, and that measurement is taken using the idea behind half-life. There's a different drug. Some of you may have heard of it as well. It's called celecoxib. I know a little bit more about this drug. The commercial name for celecoxib is Celebrex. And again, some of you may have heard of that particular medication. It is used to treat pain, usually arthritis type pain. And if you read the prescribing information for Celebrex, what it says is the effective half-life, so there's half-life again, is approximately 11 hours under fasted conditions. So if you haven't eaten anything and you take a Celebrex pill, about half of it is gone after 11 hours. So maybe if you're taking Celebrex, you might take it twice a day or somewhere along those lines, somewhere on that order. Probably 2, maybe 3 times a day. And I have a relatively interesting story behind Celebrex. I used to work with one of the chemists who helped to invent Celebrex. And for those of you who don't know the pharmaceutical manufacturing process, what happens, or the drug discovery process. So imagine a bunch of chemists are trying to create a drug that is used to treat arthritis pain. And they come up with many different versions, many different chemicals that are potentially useful in treating arthritis pain. And one of the things that they will test is they will test the half-life. They will test how long each of the candidate drugs lasts inside the body, usually inside the body of an animal like a mouse or a rat, before it's actually tested on humans. And the chemist that I used to work with told me that when they were trying to find a drug that eventually turned out to be Celebrex, they found another drug whose half-life was several months. So it was much longer than this. And he said that they were pretty excited about that fact because the idea was that, well, if they used that particular drug where the half-life was several months, then whoever was having arthritis pain would only have to take one pill maybe once a month or once every other month, and it would be a lot easier to just take one pill every month or every couple of months. And they thought this was great, and what he basically told me, however, was that a bunch of attorneys intervened and said, look, this is going to be a drug that's going to be taken by a lot of people. If anyone has an adverse reaction, if they ingest the drug and they have some allergic reaction, let's say, to the drug, we cannot tell them to sit tight for 2 or 3 months while the drug is eliminated from their system. We actually want a drug that has a shorter half-life, somewhere on the order of a day, and eventually they came up with Celebrex, where the half-life is 11 hours. The interesting part to the story, however, is that he said that they made a large amount of the longer-acting version of Celebrex, the version that had a half-life of a couple of months, and the people in his chemistry group who owned dogs, they took some of that longer-acting version of Celebrex home and gave it to their dogs when they had hip problems. And the reason being is that they felt it was probably reasonably safe enough, and that dogs prefer not to eat pills, so if they could be fed something that would sort of help them with their arthritic pain caused by bad hips, and they only had to feed it to the dogs once every couple of months, that would be much better than trying to feed them a Celebrex or an aspirin once or twice a day. So that's my story about half-life, and that is a story about Celebrex. And just another example, we won't do a problem related to this, but you can certainly do half-life problems related to medicines just as easily as you can do half-life problems that we did in the previous section for isotopes. But this, again, cocaine, I'm sure everyone is familiar with. It's an illicit drug. However, it is also a prescription medication that is occasionally used as an anesthetic, believe it or not. And if you read the prescribing information for cocaine, you see that cocaine is degraded by plasma esterases, so basically it's broken down in the blood, with half-life in plasma being approximately 1 hour. So this, believe it or not, this kind of explains some features of cocaine. And basically it explains why the high behind cocaine cocaine is relatively short, and that is because if you snort it and once it reaches your blood, half of it is gone within 1 hour. So this sort of helps explain why apparently people who take cocaine, the high doesn't last very long because half of it is gone after you ingest it in approximately 1 hour. So that, believe it or not, is the end of the nuclear radiation chapter. So we started with nuclear radiation. We talked a lot about radioactive materials and radioactive isotopes. We ended up talking about half-life, and turns out that half-life shows up in relation to pharmaceuticals an awful lot, and half-life is used to basically figure out how long medicines last when they're administered to people.